Welcome to today's refresher lecture. I'm Dr. Leslie Blankenship-Williams, and today we are going to be covering chemical bonds. And specifically, how can we tell when an atom is going to form a chemical bond? And if it forms a chemical bond, what type of chemical bond will it form? You may have heard the term, all biology can be broken down to chemistry. And today, we're really going to see why that statement exists. As we recall the particles of an atom and we go through how an atom is structured, we're going to re-explore how that particular chemical structure determines how likely that particular atom is to react with other atoms and form chemical bonds. Chemical bonds, of course, are the beginning of making molecules. When you have molecules, you can start making cell components, and from there you can make cells. So when you think about life, we can really boil it down to the chemistry in that aspect. So what we will specifically be focusing on is how does an atom's chemical structure determine its chemical reactivity, and one of the things that we'll need to explore in order to determine that is the electrons and how those electrons fill their orbitals or the electron shells. And then we'll take a look at what strategies atoms use to try to essentially wheel and deal their electrons in order to fill their electron shells. And from there, we'll look at different types of bonds that can result from these strategies, specifically covalent bonds and ionic bonds. And from there, some types of covalent bonds lead themselves to a special type of bond called a hydrogen bond. So we'll be looking at all three of those and finally finishing with a few examples of each type, focusing on hydrogen bonds. Okay, so let's start with a review of what an atom looks like. When you take an atom and you break it down into its most basic components, an atom itself can actually be broken up into its three subatomic particles. They are the protons, the neutrons, and the electrons. The protons have a positive charge, the neutrons get their name because they are neutral or have no charge, and the electrons have a negative charge. The protons and the neutrons ball together in a subatomic nucleus, and the electrons spend their time orbiting that subatomic nucleus. A rule of thumb is that if you take a look at an atom and it has a certain number of protons, it probably also has the same number of neutrons and electrons. Let's see how that relates to helium, which is shown on the slide. Helium has 2 protons. Therefore, it should also have 2 neutrons and 2 electrons. So again, the rule of thumb, however many protons that particular atom has, it probably also has the same number of neutrons and electrons. So let's say I were to show you an atom with 6 protons. How many neutrons would it probably have? 6. How many electrons would it probably have? 6. And once again, the protons and neutrons would come together in a ball in the center, and the 6 electrons would spend their time orbiting around that subatomic nucleus. Now that we've discussed that rule, let's take a look at how do we arrange the electrons. And for that, let's take a look at the periodic table that shows some of the electron distribution diagrams. If you recall, the periodic table is organized such that the smallest atoms are near the top, and as you increase the number of protons, you move towards the bottom. Here we see that the smallest atom has only 1 proton, and it's up here in hydrogen. The next smallest atom has 2 protons, and it's helium. 96% of all biological material is made up of one of these 4 atoms: hydrogen, nitrogen, oxygen, and carbon. So take a moment and find those elements on the screen. So you'll see hydrogen is way up at the top, it's very small. And then in the second row towards the center, we'll see carbon, nitrogen, and oxygen. Notice that carbon is defined by having 6 protons. So how many electrons does it have? 6. And go ahead and count the little balls that are floating around carbon, and you will see there are 6 electrons. Let's take a look again at nitrogen. Nitrogen is defined as having 7 protons. So how many electrons does nitrogen have? 7. And if you take a look at nitrogen, you can see that there are indeed 7 electrons. And then finally, let's take a look at oxygen. Oxygen has 8 protons. Therefore, it also has 8 electrons. Okay, so now that we know that the number of protons determines which element that particular atom belongs to, and the number of protons equals the starting number of electrons, let's take a look at how those electrons are arranged. You might notice from this slide that electrons are arranged in rings, almost like rings around a planet. But there seems to be some method to the madness in this sense. In other words, when we take a look at the first row, the top row or the first shell, you'll notice that hydrogen, the smallest atom, has 1 ring with 1 electron in it. You move over to helium and you see that one has 2 electrons. So how many electrons can you fit into that first ring? Only 2. And if you have any more electrons than that, you need to use another ring outside of that, as we see with the second shell. Starting with lithium, which has 3 electrons, we notice that that third electron must go into a second or outer orbital. Now, if you follow, that entire row has both a first and a second orbital, and every time it gets a new electron, it adds it to that second orbital. If we move all the way over to neon, which has 10 protons and therefore 10 electrons, we see that 2 electrons are in the first orbital and 8 are in the second. And beyond that, that second orbital can't hold any more. So if we go down to sodium, which has 11 electrons, we notice we have to add yet a third orbital. So the rule is that the first shell can only hold 2 electrons. The second shell can hold 8, and the third shell can also hold 8. Let's take a moment to draw out one of the atoms, oxygen, and take a look at how oxygen can be arranged using these rules. So oxygen, of course, is going to have 8 protons and therefore 8 electrons. Let's start by drawing the subatomic nucleus, which I will denote as just a ball with the letter O in the center, which stands for oxygen. So then my question is going to be, how do I distribute those 8 electrons? Now, in order to look at this, let's first actually make little boxes that correspond to where those electrons might go. And notice I'm drawing my boxes in a very specific way. My first shell, which I just drew, has 2 boxes to it. My second shell is going to have 8 boxes to it, placed approximately every 15 minutes from each other. But notice that I don't just make 8 random dots. Instead, I put them in pairs. So let's take a look. Using the fact that oxygen comes with 8, let's put the first 2 electrons, which I'll denote as a little dot, here in that first shell. That takes up all available space in the first shell. So that means that we started with 8, we've put down 2, and that means we have 6 left. So let's see how these 6 get distributed. We'll start here, 1, 2, 3, 4, and I still have 2 more, so I'm going to put them 5 and 6. Notice I have not completely filled this outer shell. Instead, what we see is this outer shell has opening. Specifically, there's an opening here for an electron and an opening here for an electron. Let's compare this drawing to what we see on the periodic table. When we go to the periodic table, this represents oxygen. And notice, once again, the first ring has 2, and the second ring has 6. But 2 of those 6 electrons do not have a partner or a pair. This is critical because not having a complete outer shell makes an atom chemically reactive. Another rule of thumb is that atoms are happy when they have a complete outer shell, also called a valence shell. A valence shell is another word for the outer shell. So does oxygen have a complete outer shell? And the answer is no. It needs 2 more in order to be complete or happy. So at this point, let's take a look and figure out what atoms are naturally happy or complete. And as it turns out, it's all of the atoms in this row right here. So we notice that helium is happy because it has 2 electrons and it completes its outer shell, which can only hold 2. Neon is also happy because down here in neon, we notice that neon has 10, 8 being in the outer shell, and 8 is what the outer shell can hold. And then argon with 18 also has a complete outer shell. Because those atoms have complete outer shells and they are satisfied, they are not going to be induced to wheel and deal with other atoms to try to fill their outer shells. They're happy, and therefore they are mostly chemically unreactive. However, all of the other atoms right here do not have complete outer shells, and therefore they're going to try to make arrangements with other atoms in order to complete them. So the goal for these atoms is to try to complete their outer shell somehow such that their outer shell is complete. And there's really 2 strategies to do this. One strategy is simply to say, you know what? You have an electron, I have an electron. Let's get together and see if we can make a pair that can be shared. Another strategy is to say, I have an extra electron I don't want. I'll give it to anybody. And of course, there are those atoms out there that say, I only need 1 more electron. Please give me your electron and I will be happy. So both strategies can be used in order to make these atoms happy or satisfied. So let's take a look at the first strategy, the idea of sharing. If you take an atom that only has a few that are missing, such as we saw with oxygen, which was missing 2, they might be willing to try to share a pair of electrons. So let's go back and see how oxygen might be able to do this with hydrogen. Hydrogen has 1 electron and therefore only needs 1 more to satisfy their outer shell. So down here, I'm going to go ahead and draw a hydrogen. And remember, hydrogen just has 1. Now, let's see how I draw this. I'm going to put that 1 electron right here. And voila! Hydrogen, bringing 1 of its own electrons and sharing 1 with oxygen, now has a complete set. And those 2 electrons satisfy this outer shell of hydrogen. It also satisfies oxygen's requirement to have a partner there. But oxygen isn't completely happy because we still have this missing electron as well. So what we can do is we can put another hydrogen in there. Like so. So now everybody is happy. Both the hydrogens have complete valence shells and oxygen also has a complete valence shell. So when you have this sharing of valence electrons, kind of a cooperation, we call that a covalent bond. So the co stands for cooperation and valence stands for the fact that it's dealing with the valence electrons. So a covalent bond is going to be a shared pair of electrons. And so if I were to circle the shared pair, it would be this pair and this pair. These are the shared pairs between the atoms. Now let's return and take a better look at how this works. You might wonder, why is water H2O? In other words, why is it always 1 oxygen and 2 hydrogens and not H3O or HO2? But in reality, when we see the electron structures of both oxygen and hydrogen, we realize that 1 oxygen and 2 hydrogens makes every atom happy in that arrangement. And this is a chemically stable molecule. So when looking at this slide, we see that the electron diagrams match very closely to what I drew. You may also recall that because it gets cumbersome to start drawing electron shells, a closer way to draw the covalent bonds is simply to use this structure right here, where you use a solid line to denote a shared pair of electrons. So every time you see a solid line between two atoms, that denotes a single covalent bond. Let's take a look at some other covalent bonds. In this graph here, we see that two hydrogens can share. We see that two oxygens can share. And this one's a little special because instead of sharing just a pair, those two oxygen atoms actually share two pairs, which makes a double covalent bond. We see that methane can share, or carbon can share with 4 hydrogens down here. And we see, once again, water. So if we were to go back to our periodic table and take another look at it, we would realize that carbon actually needs 4 electrons to make it happy. Nitrogen needs 3 electrons to make it happy. Oxygen, as we've just seen, needs 2 electrons to make it happy, and hydrogen just needs 1. Thus, every element has a characteristic number of covalent bonds that it's able to form. Because carbon requires 4 more electrons, it makes 4 covalent bonds. And we see that right here with methane. So notice there's 1 carbon in the center, and we can count 1, 2, 3, and 4 solid lines representing 4 covalent bonds. Nitrogen can form 3 covalent bonds. Oxygen can form 2, and hydrogen can form 1. Now that we've discussed this mechanism of sharing electrons to make every atom happy, let's take a look at another strategy exhibited by a few elements that really just need 1 more electron or would rather just give 1 away. They use a little bit different strategy. Okay, sodium and chloride. You probably know this as table salt. Sodium chloride go together. Na stands for sodium and Cl stands for chloride. If we look just at the left-hand side of the screen, you will take a look at the electron structures and notice something odd. Sodium has 11 electrons, so its outer valence shell has only 1. Now, it could say, I need 7 partners, and that's possible, but it would be really hard to find 7 people willing to cooperate with it. So it employs another strategy. It says, you know what? That outer electron, I don't want it. If I could get rid of it, then I would only have the second shell as my outer orbital, and I would be complete and I would be happy. So sodium is looking to dish off that electron. And who is a likely taker? Why? Chlorine, of course. Chlorine has 17, and it says, you know, I only need 1 more electron to fill my valence shell. And that's great. It sees sodium and goes, you know what? You want to get rid of it, I want to take it, and let's make a deal. And so sodium, instead of sharing, just says, take my electron, and chlorine says, gladly. And because of it, both are happy. But as a result, we now have an unequal number of protons and electrons. Remember, sodium started with 11 protons and now only has 10 electrons. So we have 11 positive charges and we have 10 negative charges. If you say plus 11 and minus 10, that leaves a plus 1 net charge. So sodium becomes an ion. An ion is any molecule or atom with a net charge. So sodium becomes plus 1. And as a result, chloride also experiences the same thing, but kind of the opposite here. Chloride started with 17 protons, but now has 18 electrons. So it has 1 more negative charge that doesn't have a partner. Therefore, chlorine becomes chloride with a negative 1 charge. So we have a positively charged ion and a negatively charged ion. one of the basic rules of chemistry is that opposite charges attract. So positive and negatively charged atoms, they come together and form what is known as ionic bonds. In other words, a bond between ions. So that's another strategy where you have a donation of one electron and the recipient, and when you have those charges, they get together and they form ionic bonds. Okay, so that explains the two ways to somehow satisfy your valence shells. So we've covered sharing and we've covered donating and accepting. Now let's turn to the third bond, which is really, in my opinion, the trickiest bond to look at, the hydrogen bond. The hydrogen bond isn't basically someone going, I want that electron or I want to fill my outer shell, but rather a result of special types of covalent bonds. So now that we have returned from ionic bonds, let's take another look at covalent bonds, because not all covalent bonds are equal. As it turns out, some atoms that participate in covalent bonds actually hog the electrons more so than others. And two of those big electron hogs are going to be oxygen and nitrogen. So let's take a look at how those atoms react when they are paired with a more meek atom such as hydrogen or carbon. So this again is going to be our water molecule. We notice that we have a shared pair of electrons right here and a shared pair of electrons right here in water. Because the oxygen hogs those electrons, this pair ends up spending more time in this orbital than it does in this orbital. So this pair might do something like this: 3 times around here, and then only 1 time around here. Really, it is not a 50-50 split. Rather, it spends 70 or 80% of its time around this atom. Same thing with this pair of electrons here that were shared between this hydrogen atom and this oxygen atom. As a result, the electrons are pulled towards this oxygen, and it makes this side of the molecule much more negative. So we would show a sigma and a negative to denote a partially negative charge over here. Because these hydrogens are feeling rather electron deficient, since their electron spends most of its time with oxygen, they actually look like they don't have electrons part of the time. So we call them partial positive or sort of positive. The result is going to be 2 polar covalent bonds. A covalent bond between this hydrogen and this oxygen with an unequal pull. In other words, the electrons are not shared 50-50. Same thing here. These electrons are not split 50-50. The result is going to be a polar molecule. In other words, if I draw a line here, this side of the molecule has has more electrons around it than this side does, and it creates a partial negative and a partial positive. Let's take a look at the diagram of water that shows this. Here we see a water molecule, and we see the oxygen is sucking the electrons away from the hydrogen, creating a partial negative and the 2 partial positives. I like to think of myself as a water molecule, and if I do, I would say my trunk is going to be oxygen and my 2 little fists are going to be the hydrogen. What happens is that my trunk is going to be feeling very negative because of all the electrons swirling around, and my fists, because they don't get the electrons coming around them, feel sort of positive. Remember, one of the fundamental rules of chemistry is opposite charges attract. So what do you think my positively charged fist is going to do? It's going to be seeking out negative charges elsewhere. And this leads to what is known as the hydrogen bond. Let's take a look at water, because water is capable of forming 4 hydrogen bonds with other water molecules. If we start with the center water molecule here, we notice once again we have a negative face and then 2 partially positive hydrogen. Notice this partially positive hydrogen facing upwards is attracted to a partial negative water molecule, at least the partial negative side. So again, if I was going to be a water molecule, then my partially positive hydrogens or fists would be attracted to another person off in the distance, but only to this side of them, the back side of them that would be partially negative. If they were to turn around and face me, their partial positive fist and my partial positive fist would actually repel each other. So we see, if we look very carefully, we always see a partially positive hydrogen face attracted to a partially negative, and that leads to a hydrogen bond. As it turns out, hydrogen bonds can be more than just water. They can actually be between other molecules as well. They do have to satisfy some criteria. One criteria is that you have a partially positive hydrogen. So how do you get a partially positive hydrogen? You pair it with an electron hog. Our two electron hogs were oxygen and nitrogen. So take a look at this hydrogen bond that results from water and ammonia coming into close quarters. We have a water molecule up here, and we see that we have a partially negative face here. And again, because we have the electron hog oxygen, the hydrogen becomes partially positive. And so it is trying to reach for anything that shows a kind of negative face to it. When it finds ammonia, ammonia is 1 nitrogen and 3 hydrogens. Down here, we see that nitrogen is one of our electron hogs. So that nitrogen is sucking the electrons from the hydrogens that it's paired with. And the result is that nitrogen is kind of negative. So they get together and they form a temporary and weak attraction known as a hydrogen bond. Again, a hydrogen bond is going to be between a partially positive hydrogen and a partially negative something else. So let's look at some examples to see where we do and do not see hydrogen bonds. Okay, I'm going to actually start with these 3 water molecules here. And I'm going to start with this one right up here and start by showing, okay, we have 2 hydrogens. Those are going to be partially positive, and of course this face over here of oxygen is going to be partially negative. Let's go down here and take a look at this water molecule. Once again, we first need to identify who's partially positive and who is partially negative. So we have a partial positive here, we have a partial positive here, and we have a partial negative here. Notice I have a dashed line depicting a hydrogen bond between this hydrogen and this hydrogen. Can this work? No, it cannot. This is not a hydrogen bond because we have a partially positive and a partially positive. That is not one of the criteria for a hydrogen bond. Hydrogen bonds need to be a partially positive hydrogen attracted to a partially negative something else. So these would actually repel each other and they would not form a hydrogen bond. But let's move over here. If we take a look at water oriented a different way, we see that we have a partial negative, partial positive, and partial positive. Is this capable of forming a hydrogen bond? And the answer is yes. We have a partially positive hydrogen and a partially negative something else. So they do indeed make that hydrogen bond. Now I'm going to come down here and take a look at 2 new molecules. This is methane, it's 1 carbon and 4 hydrogens, and this is water. You might be tempted to do this, but in reality, there would never be a hydrogen bond formed between this methane and this water molecule. So this is false. But why is it false? Let's first take a look at the water molecule. We know that oxygen is an electron hog, so we have a partial negative here. So we know that the hydrogen bond needs to go to a partially positive hydrogen. But this is not a partially positive hydrogen. Why? Because it is not paired with an electron hog. Carbon does not hog electrons the way oxygen and nitrogen does. Carbon is an equal partner. Carbon will split the electrons 50-50 between, so nobody gets the electrons more. It's always 50% here, 50% here. Because of that, there is no charge around this hydrogen. And thus, that hydrogen is not feeling the longing towards other negatives. So whenever you see a hydrocarbon, a molecule with carbons and hydrogens, they are probably not going to be forming hydrogen bonds. Okay, that concludes our lecture. Thank you very much, and we'll see you next time.